Hello everyone, today we are going to discuss the NCERT questions of chapter Work, Energy and Power. So the first question is the sign of work done by force. The first question is the sign of work done by force on a body is important to understand. State carefully if the following quantities are if the following quantities are wait a minute. If the following quantities are positive or negative. So the first option is work done by a man in lifting a bucket out of the well by means of rope tied to the bucket. So here the force applied by the man is via the rope. So the rope is there is a tension in the rope which is due to the man, and that is the force responsible for pulling the bucket, lifting the bucket out of the well. So in this case, the displacement is in the direction of force. So the work done is going to be positive. And the second case, we have work done by gravitational force in the above case. So the displacement is opposite as that of the force applied, that is the gravitational force is downwards and the movement of bucket is upward. So in this case, the work done by the gravitational force is going to be negative. And in third case, we have work done by friction on a body sliding down the inclined plane. So assume that this is the inclined plane and this is the body, and it is sliding down. The body is sliding down. So the friction force would be acting in the opposite direction because friction force opposes the motion. So the work done by friction force is negative because force is acting in the opposite direction of the displacement of the body. And in third case, we have work done by friction. In fourth case, we have work done by an applied force on a body moving on a rough horizontal plane with uniform velocity. So work done by the force applied on the body moving on a rough. So the case is same here. Like the surface is rough over here, and we are asked that if on a body there is a force applied F. So what is the force if the body is moving in the direction of force on a rough surface? So on a rough surface, it means that the friction is acting, but we are not concerned about the friction force direction over here. We are only concerned about the force direction of the applied force. So the moment, since the body is moving in the direction of applied force, so it is said to be positive. Now in fifth case, we have work done by resistive force of air on the vibrating pendulum in bringing into rest. So resistive force, let us assume that there is a pendulum. One instance it's swinging in the left, and other instance it's in the middle, and the other instance is swinging on the right. So when the bob of pendulum is moving towards the central position, so air is resisting and it is acting in the opposite direction. So the frictional force is always acting on the opposite direction of motion. So in this case also, the work done by frictional force should be negative. Now in second question, we have a body of mass 2 kg initially at rest moves under the action of an applied horizontal force of 7 Newton. The question says that a body of mass 2 kg initially at rest moves under the action of an applied force, horizontal force of 7 Newton on the table with the coefficient of kinetic friction as 0.1 compute the work done by the applied force in 10 seconds, and work done by the friction in 10 seconds, work done by the net force on the body in 10 seconds, and change in kinetic energy of the body in 10 seconds. So whenever we approach this kind of question, we should first consider about the all the forces acting on the body. In this case, there are let us consider the forces here. So a body is on the table, and its mass is of 2 kg. Now horizontal force of 7 Newton is acting on the body, and the frictional force is caused by the coefficient of friction, where mu is equals to 0.1. So here the forces are gravitational force and the gravitational force of 20 Newton. If we assume the acceleration due to gravity as 10 meter per second square, and the applied force of 7 Newton, and since there is a friction, so the frictional force would be the normal reaction multiplied by the coefficient of friction, and that would come out to be 20 Newton multiplied by 0.1 maximum. Now we have been given to find out work done by the applied force in 10 seconds. So for finding out the work done by applied force in 10 seconds, we need to know the displacement that the body will cover in 10 seconds. So by applying the equation of motion here, that is equals to S equals to ut plus half ATA square, where S equals to ut plus half ATA square, where S is the displacement, and U is the initial velocity, and T is the time, that is 10 seconds, and half ATA square, in which A is the net acceleration. A is the net acceleration, and T is the time duration again. So if we find out S, the value of S, that comes out to be 126 meter. So if we multiply 7 Newton with the displacement, then we get 882 joule. That is the work done by applied force in 10 seconds. Now in second case, we have work done by the friction in 10 seconds. We know the displacement, that is 126 Newton, 126 meter from the displacement equation above. Now friction force, the friction force should be acting in opposite direction. So we just need to multiply the frictional force, maximum friction force, with the displacement, and that would be equal to 246.96 joule, and net work done by the net force on the body. So net force on the body is the applied force minus the friction force, because they both are in opposite direction, and since the applied force is greater than the friction force, that's why the body is moving, and so the work done by net force is equals to 235.04 joule, and since it is less than the work done by the applied force, because there is friction force that is resisting the motion. Now delta change in kinetic energy is equals to, from the work energy theorem, we know that work done by all the forces is equals to change in kinetic energy. So here if we just add using appropriate sign of the total work done, so that would give us the delta change in kinetic energy, and that would be equal to 635.04 joule. Now the third question is, given in figure 5.11 are example of some potential energy function in one dimension. The total energy of the particle is indicated by a cross sign or on the ordinate axis, that is the y-axis. In each case, specify the regions in which the particle cannot be found, or for the given energy. Also indicate the minimum total energy the particle must have in each case. Think of a simple physical context in which these potential energy shapes are relevant. So in the first shape we have zero total energy, zero potential energy till the x equals to a, and we have certain rise in the energy at x equals to a and to a magnitude of v naught, and then the potential energy is constant. So on the ordinate axis we have been given the total energy of the particle is negative with the cos sign. So on the ordinate axis we have the potential energy. So in this case we see that the body can't have energy greater than the total energy. So the think of a special also indicate the minimum total energy of the particle must have in each case. Specify the region if so total energy can potential energy can never be greater than the total energy. So for any position in the x-axis over here the particle cannot be found. So we can simply say that this is unrealistic situation, and we have to give in each case specify the reason in which the particle cannot be found for a given energy. So in any of the point of x particle can't be found because the total potential energy can't surpass the total energy. In the second case we have a step curve. Again in this case we will apply the same rule, that is if total energy is greater than the potential energy we can say that the particle can't be found over there. And since in this case we have in minus infinity to plus infinity, we see that potential energy is higher than the total energy. So again the particle can't be found in any of the points over here. And in this case, the third case, we can see that the particle is having energy less than total energy in some regions, like from minus infinity to b by minus b by 2, and from a by 2 minus a by 2 to plus a by 2. So in this region we can say that the particle can be found, and likely in this region also. So here the concept is if total energy is equals to kinetic energy plus potential energy. So whenever we have been asked about in certain situation, we will consider this while answering the question. So in fourth question we have the potential energy function for any particle executing linear simple harmonic motion is given by half kx square, whereas k is the force constant of the oscillator. For k equals to 0.5 Newton per meter, the graph of Vx versus x is shown in the figure 5.12. Show that the particle of total energy 1 joule moving under the potential must turn back when it reaches x equals to plus minus 2 meter. So the definition of conservative force is that it can be derived from the scalar quantity potential function, that is fx equals to minus dv by dx. Now here dv is the differential of the potential energy function that has been given, and it is equals to kx square by 2. So as per the question, Vx equals to kx square by 2, the derivation would be equal to minus kx, which is the spring force. Now the total mechanical energy of the system is conserved. So the summation of kinetic energy and potential energy is always equals to is always constant for the conservative system. So here when we see that the particle reaches to a maximum position, so in order to conserve the total energy it must stand back, or the potential energy must be converted into kinetic energy. It can't surpass this. Total energy is equals to kinetic energy plus potential energy. Now the fifth question is the casing of a rocket in flight burns up due to friction. At whose expense is the heat energy required for burning obtained? The rocket or the atmosphere. The casing of a rocket in flight burns up due to friction. At whose expense is the heat energy required for burning is obtained? The rocket or the atmosphere. So since the rocket rocket's motion is being resisted in this case. So obviously it's the rocket's at the rocket's expense the casing is destroyed. Now the second question is, comet move around the sun at in highly elliptical orbits. The gravitational force on the comet due to sun is not normal to the comet's velocity in general, yet the work done by gravitational force over every complete orbit of a comet is zero. Why? Because this is governed by the conservative force, and the conservative force is not a path function, it is a state function. So once the state is once the cycle is completed, so the work done by gravitational force is going to be zero. The third question is, an artificial satellite orbiting the Earth in very thin atmosphere loses its energy gradually due to dissipation against the atmospheric resistance, however small. Why then does its speed increases progressively as it's come closer to the Earth? So its potential energy is slowly converting into kinetic energy, and that's how its speed is increasing. Now in fourth case, we have in figure 5.13, the man walks 2 meters carrying the mass of 15 kg on his hands. In figure 5.132, he walks the same distance pulling the rope behind him. The rope goes over the pulley and the mass of 15 kg hangs at its other end. In which case is the work done greater? So we see here that in the second case the work is done against gravity, and in the second case the work that is the force applied by the man is resisting gravitational force, and its potential energy is increasing. So obviously in the second case the work done, the calculated work done would be higher than in the first case. Sixth question is, underline the correct alternative. When a conservative force does positive work on the body, the potential energy of the body increases or decreases, remains unaltered. So when the conservative force done is positive, so here in this case let us assume that the ball is falling by the influence of gravity, and we know that potential energy is given by mgh. So h is the height of the body. So when the ball is falling due to the action of gravity, obviously due to falling, h would decrease. So here the potential energy will decrease, and the work done by the conservative force here in this case is the gravitational force is positive. So we see that when the work done by conservative force is positive, then the potential energy will decrease. Now in the second case, we have work done by a body against the friction always returns in loss of its kinetic energy or the potential energy. So work done always resists the motion of the body, thus the kinetic energy of the body will loss. The third is, the rate of change of total momentum of many particle system is proportional to the external force or the sum of the internal. So internal forces of the system, the total momentum is always conserved. So here the case should be external force. Now in an elastic collision of the two bodies, the quantities which do not change after the collision are the total kinetic energy or the total linear momentum. So linear momentum is conserved, and also the total energy of the system is conserved. So in this case again the total linear momentum would be there and the total energy of the two body would be there. Now in seventh question, we have state if each of the following statement is true or false. Give reason for your answer. The question is, in an elastic collision of two bodies, momentum and energy of each body is conserved. So if we take the reference for each body, then obviously it is not going to be conserved. The system momentum is conserved in this case, so obviously it is going to be false. Now in second case, we have total energy of the system is always conserved no matter what internal and external forces. So total energy of the body does depend upon the external force, so it is going to be false. Now work done in the motion of a body over a closed loop is 0 for every force in nature. This is only true for conservative force, so this is going to be false. Now in an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. So in certain cases this can't be true, but it is mostly true. Like when in the nuclear reactor, this is not possible, this is not always correct, but in most of the cases this is going to be correct, because no energy generation takes place, only dissipation takes place for an inelastic collision. Now in 8th question we have answer carefully with reasons. In an elastic collision of the two bilbard walls, the total kinetic energy is conserved during the short time of the collision of the wall, that is when they are in contact. Actually, when they are in contact, the total kinetic energy is not conserved. The second question is the total linear momentum conserved during the short time of an inelastic collision between two bodies? That is also true. The third question, what are the answers to B and 4? If the potential energy of the two bilbard balls depends only on the separation distance between their centers, is the collision elastic and inelastic? So here we are talking about the collision of the body, and we know that for elastic collision the momentum is conserved, that is m1 v1 plus m2 v2 is equals to m2 v1 plus m1 v2. So here the concept used is that only. And the ninth question we have, body is initially at rest, it undergoes one-dimensional motion with constant acceleration. The power delivered to it in time t is proportional to. So here power delivered, when we are talking about power delivery, then we are concerned with not only the motion but its velocity as well. So if equals to mass into acceleration, and work done is equals to force times distance, and distance here can be represented as ut plus half at square, and since the body was initially at rest, so s can be given as half at square. Now the expression for work done would be equal to ma times half at square. Now work done is now if we take this quantity as constant, because mass is constant and acceleration is also going to be constant, then work done is directly proportional to t square, and if we take the derivative of it, then it is directly proportional to t. So the answer would be second in this case. The ninth question is the 10th question. The body is moving unidirectionally under the influence of source of constant power. Its displacement in time t is proportional to. So here it is given that the body is moving under constant power. So constant power is equals to, power is the time derivative of work done. So here dke by dt is equals to constant. So if we derive the kinetic energy with respect to time, we get that it is equals to mv dv by dt, and that is equals to constant. So if we integrate both the sides, we see that v is equals to v is proportional to k t raised to the power of 1 by 2. Now if we integrate both the side with t, because we have to find out the displacement, so it would be equal to the displacement would be proportional to t raised to the power 3 by 2. So here third option is going to be correct. Now in 11th question we have, a body constrained to move along the z-axis of a coordinate system is subjected to a constant force F given by where I, J, K and unit vectors along the x, y and z axis of the system respectively. What is the work done by this force in moving a distance of 4 meter along the z-axis? So here, since the motion is along the z-axis, so the component of displacement vector in the I and j is going to be 0. Now we can use the expression for work done over here as F dot d, the scalar product of force and displacement. And since the displacement is 4 meter along the z-axis, so it can be written in the vector form as 4k cap. And if we take the dot product of these two, then we will get the 12 joule, which is the answer. In question number 5.12, we have been given, and the electron and proton are detected in a cosmic ray experiment. The first with kinetic energy of 10 kilo electron volt, that is that of the electron, and the second with 100 kilo electron volt, which is faster, the electron or the proton. Obtain the ratio of their speed. So we have been given the ratio of kinetic energy of electron and proton. So the ratio of kinetic energy of electron to proton is 10 to 100, and we have to find out ratio of their speed. So we know the expression for kinetic energy, that is half mv square. For electron we will use half me, that is the mass of electron, times the velocity of electrons squared, and similarly for proton is vp square. Now we take the under root of ve by vp, then we get the value of 13.5, that is electron is 13.5 times faster than that of the proton. And that's because the mass of electron is less. So in 13 number question we have a raindrop falling with a radius, raindrop of radius 2 millimeter falls from the height of 500 meter above the ground. It falls with a decreasing acceleration due to viscosity resistance until at half its original height it attains the maximum terminal speed and moves with a uniform speed thereafter. What is the work done by the gravitational force on the drop of the first and the second half of the journey? What is the work done by the resistive force in the entire journey if its speed on reaching the ground is 10 meter per second? So here the journey of raindrop is considered. So it is falling from a height of 500 meter. So here in this question, the concept that we are going to use here is the work energy theorem. And work energy theorem, we all know, it says that the work done by all the forces is equals to change in kinetic energy of the body. So here the forces that are acting is gravitational force and the resistive force, that is the resistance due to friction. So we have to find out what is the work done by resistive force and what is the work done by gravitational force in the entire journey. So if you want the solution, you can refer to this question from my video over here. In the 14th question, we have a molecule of a gas container hits the horizontal wall with the speed of 200 meter per second. An angle of 30 degree with the normal and rebounds with the same speed. Is momentum conserved in the collision? Is the collision elastic or inelastic? So here we have to use the concept of collision, the elastic collision and inelastic collision. So the molecule and the wall system will always be conserved because this is the system, and initial and final speed of the molecule won't change as the rebound speed of the wall is 0. So no energy is dissipated or transferred to the wall. So the kinetic energy of the system is also conserved. Thus the collision is elastic. So in 15th question, we have a pump on the ground floor of the building can pump the water to fill up the tank of volume of 30 meters cube in 15 minutes. If the tank is 40 meter off the ground, the efficiency of the pump is 30 meter. How much electric power is consumed by the pump? So here we have to use the concept of work done and also the power. So the concept of work done here is the water has to be lifted 40 meter above the ground, and how much water is to be lifted is hinted with the volume of the tank. that is this much quantity of water. We have been given the volume of the tank, and this much volume of the water has to be lifted, so we can calculate the mass that has to be lifted. And since we know the mass and we know the acceleration to gravity and we know the height to which it has to be lifted, that is 40 meters, so we can calculate the change in potential energy, or the pump will work against the gravitational force to for the water to achieve that potential energy. And also we have been given, so with that we can know the work done by the pump, and for how long will that work be done is 15 minutes. So we can find out the rate of power delivery per second, and that would be equal to power in watts. So here, upon calculation, you can refer to the video of this question over here. We get the value of power is 43.55 kilowatt, considering the 30% efficiency. So the section question is, two identical ball bearings in contact with each other and resting on a frictionless table are hit head on by another ball bearing with the same mass moving initially with a speed v. If the collision is elastic, which of the following is possible result of the collision? So here we see that two identical ball bearings are there in contact with each other, that is 2 and 3, and resting on the frictionless table are hit head on by another ball bearing, that is 1 comes and hit the 2 and 3. So what would be the possible case? So here the collision is elastic, so we have to find out which of these cases can be possible. So here we have to look the reason or the why, what are the cases under which the elastic collision happens, or what are the properties of the system when the elastic collision happens. So in this case we can see that the kinetic energy should be conserved of the system. So in this case the final kinetic energy of the system and initial kinetic energy of the system will be evaluated. So upon evaluation in all these three cases, the initial kinetic energy is going to be half mv square. The mass of each ball, if considered, is m, and the velocity is v, then it would be equal to half mv square. Now initial kinetic energy must be equal to the final kinetic energy. So in all these three cases we see that only the second case follows this rule. In first case also it is the less kinetic energy that we get after the impact, and in third case also it is the less kinetic energy that we get. Only the second case represents the conservation of kinetic energy, so only the second case is going to be correct. So in question number 17 we have above A of pendulum released 30 degree from vertical hits another bob B of the same height as the rest. The table as shown in figure 5.15. How high does the ball A rise after collision? Neglect the size of the balls and assume the collision to be elastic. So the collision is elastic. So there are two things that is going to be happen. That is, the initial kinetic energy of the system is going to be equal to the final kinetic energy of the system, and here system is by system we refer to the ball A and B, and since there is no friction on the surface B, so no energy is going to be lost, and initial momentum is equals to final momentum. So by this expression we can find out the the final velocity of first and second ball. So the second ball final velocity comes out to be 2 mv by 2m, that is equals to v. So the entire energy of ball A will be transferred to ball B, and ball B travel with the velocity v. And the question number 18 we have a ball above of pendulum is released from a horizontal position if the length of the pendulum is 1.5 meter. if the length of the pendulum is 1.5 meter, what is the speed with which the bob arrives at the lowest point? So given that dissipated 5% of its initial energy against the air resistance. So again, here we will use work energy theorem. The potential energy is the initial potential energy is going to be mgh, that is mass into acceleration to gravity into height, and height is 1.5 meter. The kinetic energy after loss would be equal to, after 5% loss, that is only 0.95 times the potential energy would be there. So we know the final kinetic energy of the body, that is equals to 0.95 times the initial potential energy. So since we know the kinetic energy final, we can equate it with half mv square, where v is the final velocity of the bob, and thus we can calculate the velocity, final velocity. Now in question number 19, we have been given a trolley of mass 300 kg carrying a sandbag of 25 kg is moving uniformly with a speed of 27 km per hour on a frictionless track. After a while, the sand starts leaking out of the hole on the floor of the trolley at the rate of 0.05 kg per second. What is the speed of the trolley of the entire sand is empty? So here again, the conservation of momentum is applied. Now assuming trolley and sand to be the system under consideration, no net force is acting on the system, so the truck won't change its speed, and also if the sand is falling, then it would continue with the same speed. So there is no any change in speed because there is no any external force acting on the system, thus the momentum will be conserved. Now in 20th question, we have a body of mass 0.5 kg travels in a straight line with velocity given as a function of x, where a constant is also given. What is the work done by the net force during this displacement for x from 0 to 2 meter? So we have been given the expression for velocity, and we have to find out net work done. So we know that velocity is the derivative of time, and we have been given the velocity as, so we can find out the acceleration from the expression. If we differentiate velocity expression with time, then we will get the acceleration of the system, and once we get the acceleration of the system, we have been given the mass, so we can get the force of the system, and once we get the force of the system, we only need the function of its position, and once we get the position, we can simply integrate for the limit of x equals to 0 to 2 meter, and we get the value of 50 joule. You can refer to the solution for the detailed explanation. So in 21st question, we have the blades of windmill sweeps out area of A if the wind flows at a velocity v perpendicular to the circle. What is the mass of air passing through the time t? What is the kinetic energy of the air? And assume the windmill converts 25% of the wind energy into electrical energy, and A is 30 meters square, V is kilometer per hour, the speed of the wind, and density of air is 1.2 kg per meter cube. What is the electrical power produced? So here we have been given the area of cross section and the velocity, so we can get the volumetric flow, and since the density is known, we can get the mass flow rate, and since the mass flow rate is known, we can get the kinetic energy that is passing, and the kinetic energy that is passing per unit time, and since we haven't given the efficiency, we can calculate the exact power that can be produced, and thus we get all the quantities that has been asked for. What is the electrical power produced? So here the information flow is like we have been given the cross section and the velocity of the wind. So here if we multiply these two things, we will get the volumetric flow rate, and we know that from volume we can calculate the mass by multiplying it with density, and similarly once we get the mass, then we can get the energy as well, kinetic energy, it is mass times velocity squared, and since we get the energy throughput, we can get the power, and since having the efficiency known, we can calculate the exact power that is being produced. Now in 22nd question, we have a person trying to lose weight. Dieter lifts 10 kg mass 1000 times to a height of 0.5 meters each time. Assume that the potential energy lost each time she lowers the mass is dissipated. How much work does she do against the gravitational force? Fat supplies 3.8 into 10 raised to the power 7 joule of the energy per kilogram, which is converted to mechanical energy with 20% efficiency rate. How much fat will the dieter use up? So we have been given the fat that is consumed in each cycle, and we also have been given the total number of cycle, that is 1000 times. So we have to calculate how much work she does against the gravitational pull. Here the work done against the gravitational force is when she lifts the weight, and that is when the fat gets burned up, and we can easily calculate it using the potential energy mgh. So here it has been calculated, and you can refer to it for detailed explanation. The third question, in the 23rd question, we have a family uses 8 kilowatt of power. Their direct energy is incident on the horizontal surface at an incident of 200 watts per square meter. If 20% of this energy can be converted into useful electrical energy, how large an area is needed to supply 8 kilowatt? Compare this area to that of the roof of the typical house. So this is a question of arithmetic. That is the incident power we are getting is 200 watts per meter square, and output efficiency is 20%. So we can get the output power, and once we get the output power, we can get the actual roof of the house when required power is given, that is 8000 watts. So we also get the roof area required, that is approximately about 200 meters square. And since we can get the value of roof dimensions approximately, and that would be equal to 14.14 meter. So if we get a roof of 200 meters square, we can generate power of 8000 watts under the given conditions. So the NCERT discussion is concluded. If you have any questions, you can always post to the given links, and it will be discussed. Thank you.